So lately we've been studying more of kind of like algebra topics, and that's true. We will bounce back into some other specific sort of pre-calculus topics till the end of the year, but we're still kind of in this algebra sort of theme. And what we're going to do now, instead of solving special equations, is everybody's favorite, we're going to graph some special equations. So everyone in unison, one big moan, we're going to be graphing. It doesn't have to be that bad, though, especially because we're going to be graphing, again, some specialized equations. Now, actually, just as a little bit of a preview, honestly, I don't think you have to copy this down, but you can if you want. But as a little bit of a preview, I want to show you some of the graphs that we're going to be looking at. And then as we come back to them in the next few weeks, you'll be like, oh, yeah, I at least saw that a little bit. Here's one that looks like a bucket of fun. I actually typed it in ahead of time, again, not maybe to save you a few moments, but I've got this 6 minus the square root of x squared minus 4x plus 12. What the heck is that going to be? It actually just turns out to be a nice little semicircle. It's a nice little semicircle, or it kind of looks like something like a skateboarder might kind of go back and forth on, but it truly is an equation. It's a circular equation, and you'll come to know why the numbers in that equation give you a certain center and a certain radius. So you'll have to come back for that. Here's an equation that's also very specialized. It's not like the other one, but it is kind of look like some that we've solved. It's obviously a rational equation. Again, I typed it in ahead of time. Now, you may have had some exposure to rational equations, or maybe not too much. It depends on algebra and other things in the past, but it's not a heartbeat, but it does kind of get like these branches. And there's this branch to the left, but it's approaching an asymptote, which you've seen before, a vertical asymptote. Now there's this branch to the right, which is also approaching a horizontal asymptote, if I can kind of get this in here. Okay, so there's asymptotes on these guys, and we're going to figure out where they are and why they are. There's actually something else in here that's very intriguing. There's a hole in the graph. The calculator doesn't show it, but literally if I was walking along that graph, I would fall into a hole, and I would disappear to undefined, never to be found again, until I get back up out of the hole and then keep on walking. But there's literally a hole in the graph. That's a mathematical idea that we, not surprisingly, will also figure out why and where and some other things with it. And not to be unmatched, we have this one, which actually will be the one we talk about today, and is probably not a brand new graph. It's just special and very important. And of course, it's a quadratic, it's a parabola. And maybe you're saying, yeah, I kind of, now that you mention it, would have known that that was going to be a parabola, but we still are going to spend a day just kind of making sure that you're comfortable with the pieces of a parabola. Because honestly, parabolas are probably one of the most sort of applicable graphs to sort of life, in that they always involve, or I should say gravity always will connect back to a parabola. Gravity, as you study in physics, always connects back to an equation with an x squared. So what we want to do in math is maybe do more of the mathematics behind a parabola. So you can go upstairs in science and you can kind of say, oh, that's why the teacher gave me that equation on my equation sheet, or some other applications of parabolas. So even though I graphed everything on the calculator there, maybe it's not a big surprise to you also that our ultimate goal is going to be to take away the calculator. Sometimes we'll use the calculator to get started, but all these graphs, by the time we get to like the end of each topic, is going to be no calculator. Today's topic will actually just start without a calculator because you're not going to need it. At least I don't want you to feel like you need it. So let's talk about quadratic functions, and we'll call this topic 9.1. I expect that most of the things that you're seeing here that you feel like, yeah, I've kind of heard that before, but again, we're just going to brush up on it. So what do you think? We've got two forms of a quadratic. They are very important. Vertex form and then standard form. And they both kind of have their time and place. Maybe it's kind of obvious, but vertex form, it gives you a vertex. And it's important that you remember, as a math student at this level, that anytime you have something added or subtracted on the inside, that's always a horizontal shift. That's the horizontal shift of the vertex. And then the number on the outside is the vertical shift. So basically, we're talking about a vertex that went left or right, or up or down, and it's really easy to find it in vertex form. The letter A is just a dilation number. Remember, it like stretches or compresses your graph. And then we have standard form, which we've kind of seen already this year, but it's just a different version of multiplying out or foiling out those terms. Okay, now, when we graph a parabola, I like to use something I kind of coined as the 5-point method. And the 5-point method basically focuses on the most significant 5 points of a parabola. As I sometimes say, you can jot this down if you want. It's probably not a bad idea. I think you're going to find out in about 10 minutes, though, that these 5 points would have naturally been found anyway. And that's what we're going to do when you're ready. We're going to find these 5 points so that we can get a nice little graph. We've got the vertex, it's probably the most important point, the y-intercept, the x-intercepts. Make sure you interpret point 3 and 4 as the x-intercepts. And then we've got the symmetry point. Again, I really think all of them you'll feel pretty natural, but let me give you a little guidance, and then we'll even set you loose on a problem. Get yourself a nice little parabola. This is the equation that actually I used in the quick intro, x squared plus 6x plus 4. You kind of already saw the parabola, but let's go back and kind of tear it apart a little bit. X squared plus 6x plus 4. Now actually, you look at this equation, you look at the stuff that's up here, and you might say, so what do I do? How do I get the vertex? Well, there's 2 ways to get it. And I'm going to actually push this first way. I'm going to sort of push you into making this equation look like it's in vertex form. How are we going to make it look like it's in vertex form? We're going to complete the square. Again, I'm kind of pushing you this way just because it's not always students' first thought, but it's pretty nifty. Look, if you complete the square like we've done before, you just need that perfect number. Half of 6 squared. Half of 6 squared is the number 9. Now, of course, I'm going to add 9. I have to subtract 9. That's kind of the way it works. But suddenly you get your equation to be in a different form. The quantity x plus 3 squared, and then minus 5. And ta-da, the vertex just kind of just comes forth. Now, be careful. The vertex is not 3, but rather negative 3. Remember, you shifted to the left 3, and of course, down negative 5. Well, that's nifty. Again, you can change it to vertex form. Let's go after the y-intercept. Most people don't mind a little y-intercept now and then because you just got to plug a 0 in for x. As I sometimes show, if you just plug a 0 in for x, lots of stuff becomes 0 plus 4. 0 plus 4, of course, is 4. Now you'll notice I plugged it back into the original equation. If you plugged it back into the completed equation, you get 9 minus 5. 9 minus 5 is still 4. See, when I say you don't need a calculator, we mean like no graphing calculator and also trusting some mental math. Now, you plug a 0 in for y, usually that requires a little more algebra. When you plug a 0 in for y, you're actually setting the equation equal to 0. I know you've heard that before. We did that numerous times in the last couple weeks. But look, your equation's really easy to solve in this format. I hope you're adding 5 and taking the square root of 5, and maybe some of that you're just doing in your head. But I'll show it here, because don't forget, you get plus or minus, and then you have to subtract 3. So we end up with a conjugate. We end up with -3 plus or minus root 5. Now, it's important to remember that those are x-intercepts. Before you say, well, can I get the decimal value of those? I mean, you can, but I'm trying to get you to a point that you don't need to understand what's going on. So let's go make a graph. I know we didn't finish the 5 points, but a lot of times the 5th point is more easily found by analyzing your graph anyway. So we've got a vertex at -3, -5. I want to spread this out a little bit. Anyway, it's just a sketch, but we've got -3, -5. And so we've got a y-intercept way up here at 0, 4. Just by the way, when you guys do this for a grade, you can do a couple different things. You can label your points on the graph, like I'm kind of doing here. You can just label your points in a list, or you can do both. Okay, but you have to show that you have plotted these points, and I'm labeling them so that you can see they're not just random. Now, I just drew a parabola, and I should say to you, do you feel comfortable with that? Could you just draw a parabola with 2 points? I want you to be able to do that, because the vertex obviously is that maximum or minimum, and then you know it's going to pass through the y-intercept. I mean, what else can it do? It has to open up. I suppose we could have noted that it opened up because of the leading coefficient, but drawing that parabola without any other information, I think is you should have that skill, because now it makes it a lot easier to understand these x-intercepts. These x-intercepts, remember, was this goofy conjugate. But the one on the right has to be the larger one, so it has to be the one with the plus. The one on the left has to be the smaller one, so it has to be the one with the minus. Even though we're not going to turn those into decimals, we can still be confident which one is which, because one's bigger and one's smaller, one's plus and one's minus. So we've got 1, 2, 3, 4 points. Let's go for this symmetry point. If you're wondering what's up with the symmetry point, remember that every point on a parabola is symmetrical, because, of course, you have the axis of symmetry. And the axis of symmetry then shows each side as being the same. I'm going to say, let's find this point right here. Notice that it is directly across from the y-intercept. Okay, again, it's an easy point to find because it's going to be symmetrical with the y-intercept. So a little bit of simple thinking about this distance, whether you show it or just think it, it's certainly -3 related to the vertex. And so we just need -3 more. Your symmetry point is usually found just by thinking about symmetry. Okay, so I went over -6, and I'm still at a height of 4. Again, I went over -6, but I'm still at a height of 4 because I'm symmetrical with the y-intercept. So that'll round out our 5 points. Let me give you one that I want you to try, but I want to direct you in just one way before you run the rest of the way. So -x squared plus 6x minus 8. I just want to direct you a little bit with the vertex. because we've got this second kind of thing up here. It's like a formula. It says the opposite of b over 2a. I want you to know what's up with that. It's actually a really nice formula. It's usually pretty easy to use as long as you understand what it's doing. So if you were going to use the opposite of b over 2a method, which again I'm kind of pushing here, then, well, we would have -6 over 2 times -1, just kind of following the little formula. But out pops the x value of the vertex. Okay, bless you. That's kind of nice, but you have to realize that you then would need the y value. And of course, y values come from plugging in x values. And this is kind of the spot that I want to try to set you loose a little bit, that you would think a little bit about that arithmetic, plugging 3 back into the equation so you can get that y value. And this would be what would be necessary if you were going to use that little formula. I hope you're thinking about this math. Be careful. It's a common question. Are you squaring 3 or -3? I'm trying to make it really clear that you're squaring 3. After you square 3, then you make it negative. You want to see if you can find the 5 points? Just be careful with the rest of this vertex, because it is the most important point. I see some of you with a y value of 1, -1, and I think I see maybe a 14. It should be coming out to be 1. It should be coming out to be 1. Try to make a sketch. Can you put it all together? Sometimes the x-intercept is a little finicky here because of the negatives. Please be mathematically comfortable with getting rid of the negatives. I have to be honest, I don't want to stare at that negative x squared. Now, you can, but if you just multiply through by a negative, you can make the equation something much, much easier. If you didn't think about it, that is, if you were using the quadratic formula, there's nothing wrong with the quadratic formula. Just trying to show you that the problem can be factored if you want to take it that way. Does it look like a parabola? Do the numbers do the points actually flow that way? So, you can kind of check everything as you go through here. How's your x-intercepts? 4, 0, 2, 0. Careful, don't say something silly like 4, 2, but rather it's actually points. This problem, if you're careful about the negatives, it really is almost too nice. It's too perfect. Everything is how it's supposed to be. In other words, the parabola just has to open down course, you knew that from the beginning, right? It was going to open down, but it even looks symmetrical as you look at these x-intercepts. Yes, the x-intercepts are symmetrical, but I want you to find another symmetry point. We almost always make it the point that's across from the y-intercept. Okay, it's just the easy one to find. Make sure you're thinking about the vertex distance of 3 to help you slide over here to 6, but stay at -8. 6, -8 for that symmetry point. Okay, now this stuff's nice. Maybe a lot of you are like, that's fine. It's nice doing a little bit of math, but really, what's the point of this if we don't do something with it? Most of the time, we're trying to apply these things. So I want to jump into I want to finish with 2 applications that I hope that you say, yeah, that's kind of reasonable. Both applications involve quadratics, but really they involve thinking about the 5-point method as it would apply to each scenario. Are you ready to look at the 2 apps with me? Is there anything that happened here? Are you guys sure you're okay with the x-intercepts? Being careful about the negative signs. Okay, well, here's app number 1. I know there's some words and stuff up here, but just read it first before you maybe copy something down. Because I think we can get the essence of this problem with just a few simple notes. Okay, we've got an equation that models the pathway of some projected object. Pretty common projectile motion. Okay, and we're trying to find a height that it's hit, and we're also looking for a horizontal distance. Now, people sometimes get concerned, do I have to do this without a calculator? What I'm really trying to do is get you to think about the 5-point method instead of just typing this into your calculator and trying to look at a pretty picture. I'm trying to get you to analyze the same way we just did. So if we have to use a calculator to multiply some decimals or something, okay, that's fine. But if you look at question number 1, all we have to do is just really think about which number in this equation would represent a starting height. Okay, and a starting height or a starting value is almost always a y-intercept. In fact, if you think about what's going on with this graph, even though we didn't do a lot of analysis, yes, it's going to start at 3, so I can be sure of that. Yes, it's going to open down. Okay, now I'm kind of pointing out like the 2 important things here. This graph opens down, it starts at 3. Well, you've seen enough parabolas to know that if a parabola is going to open down and it's going to start at 3, then that's what it's got to do. So we even drew a sketch without, coming up with any numbers except for 3, which again is that starting height, obviously connected to the y-intercept. So I think this thing is supposed to be in feet. That's kind of my bad. It didn't say feet, but we can put that label beside it. Okay, now the problem is supposed to be realistic. So yes, we have a baseball player, and that's where he slaps the ball just to, again, get yourself in position. Now, I don't think the rest of it's to scale. I'm pretty sure the ball went a lot farther than just out here a couple feet. Okay, which is really what question 2 is. Question 2 is, how far out did this thing go? How far out did the ball travel? Remember, the questions always relate back to one of the 5 points. So you want to be saying, I need the x-intercept. Okay, we need that, again, that distance is really the x-intercept. Let's think about the x-intercept. Okay, again, as I said, I don't want to get in a squabble about no calculator. We're going to need a calculator to get this x-intercept. What I'm really trying to do is get you to realize that we can still use equation thinking to come up with that solution. Okay, so we're solving the equation equal to 0. Again, something that's happened many times. Yeah, probably the quadratic formula is where you're going to go here. I'm going to skip a step just to save a few minutes, but I trust that you guys can do the opposite of b, plus or minus. It turns out that it's going to be the square root of 1.0384. Again, that's the discriminant, so we get 10384, and it's all over 2a, which is going to be 2 times this small number, negative 0032. Now, you do the square root of that with a calculator, you get 102. You double the bottom, might not need a calculator for that, but you double the bottom, you get negative 0064. Can we have a little conversation about how to get the final answer from, something that looks like this? We want to understand that this distance out here has to be positive. Okay, I know you guys know that you're going to add and subtract 102. If you think about it, that means we want the final answer to come out positive. And the only way that's going to happen is with the subtraction. Okay, the only way it's going to happen is with the subtraction, because when you subtract these two numbers and divide by a negative number, well, then that is going to come out positive. So I'm doing a little bit of just thinking ahead, that I don't really need to do the adding. It's funny, I actually don't want to do the adding because I want this number to come out negative, so that when I divide it by this negative, again, I end up with a positive. It actually comes out to be positive 315, a pretty nice slap there of the baseball, but I don't need the negative answer. The negative answer would have been the one back here, which isn't going to make sense for this problem. I know I went a little quickly. I know if you were doing this on your own, you'd have to process some of the decimals. I'm really just trying to make you think about what makes sense for a word problem. In this case, it's the x-intercept that matches number 2. One more. It's a classic, but hang in there with me. We got one more application problem that I always like to show on this day. It's a classic. In a math setting, we would call this a max-min problem. Same thing. I don't know if you have to get bogged down with copying down all the sentences. I mean, if you don't want to do that, let's just think a little bit about what's written up here. It seems like we've got 200 meters available. I think we can note that 200 meters available. We also, with just a drawing, can probably get the idea of what we're really trying to do. And that is, we're trying to make a rectangle. We're trying to make a rectangle. But one of the sides, although I don't recommend this probably for herding animals, one of the sides is a river. So we only need a 3-sided rectangle. Okay. Now it's common to look at this and be like, where do I start? Like, what? I feel like I don't know anything. It's actually where you want to start, with what you don't know, and be able to say that since you don't know these two sides, you have the right to call them x, but now you're on to something because you've said that they're equal. And yes, I kind of provided that input, but that is a great starting point. Both those sides are equal. I know they're not drawn perfectly, but now we can start to describe some other things about this rectangle. Now, before you say, well, should I just call that y, x and y? Let's not get another variable involved. Let's think a little bit about how much fencing it took to go around this thing, how much I used, and how much is left. How much did I use if I used x and x? It is. So I used 2x. I had 200. Now it's 200 minus 2x. Now, if you were kind of like, I don't even know like where I was going to go with this problem, I wanted to get to this point. I wanted you guys to realize that I now have dimensions. And the place we were headed in this problem all along was to find a maximum area. And the cool thing about area, even if it's maximum area, but the cool thing about area is it's just length times width. So the place where this thing was headed all along was to multiply these two dimensions, length times width. I don't care which one you want to call the length and the width, but I do care that you multiply them. So we want to find a maximum area. That means we need dimensions. Now we have a formula. And the reason this is a classic is because the formula, well, once I distribute it and so forth, the formula is quadratic. Do you see? Do you see the x squared? It's actually 200x minus 2x squared. But again, that's a quadratic. Now you'll see a problem like this again in calculus. You actually investigate it using a different pathway, but it still leads to the same place, and that is a parabola. In fact, if you think about it, it's a parabola that's opening down, and every parabola that I've ever seen that opens down has a maximum. So what I'm trying to basically direct you to is that we need the vertex. That's what this problem is really all about. We need the vertex. Feel like we have a way to find a vertex? We have two ways, right? Okay. Unless you want to complete the square, it's maybe just as easy just to do the opposite of b. Now be careful because b is 200, but the opposite of b over 2a. And that's really the way that is recommended in this problem. We're almost done. We have x for our vertex. Now this is the point in the problem where you want to realize just what 50 represents. And it literally represents, as it says, it represents x. So it represents these two dimensions. And a student that's a little more visual would say, geez, if these two dimensions are 50, then this dimension over here is got to be what's left. Okay, so it's got to be 100. A student that's a little more algebraic would say, I thought I was supposed to plug 50 back in. Okay, what happens if you plug 50 back in? Well, you get the same thing. It's just you get some bigger numbers until they subtract to still be 100. Okay, so the bottom line here is I have a 50 by 100. If I'm going to bound it with a river. And I think the question just says what's the dimensions, but obviously if we have the dimensions, we could also find the area. We could actually multiply them to be 5,000 square meters. I'm going to multiply them just to, since we can. The max-min problem. A maximum or minimum is always a vertex. It obviously just depends on what shape, what direction the parabola is going. Okay. Not all brand new stuff, I know, but trying to brush up a little bit, spend a little bit of time with the homework. Page 95 and following, because you've got some problems early on, and then the problems get into the 60s. Use my directions for those first three problems, which is to use the 5-point method. I think the book says something about graphing on a calculator. We actually don't want to do that. I want you to try to graph it without a calculator.